here we are going over the acid-base titration graph lab question worksheet, which is really a question that was on the 2015 part 2 of the AP Chemistry. So this is a very good question for us to go over because this will be a lot like our exam, okay? Because it really takes into consideration titrations, and titrations are a laboratory, very important laboratory procedure that takes into consideration all of our acid-base skills. So we put everything together with these types of problems. So let's get started. So in the question, they give you potassium sorbate, something you may not recognize, but that's okay. We can break this down. All right, I see the K in front, so it screams to me that probably gives off a K+, and it does. But let's continue reading. Is commonly added to diet soft drinks as a preservative. Chemicals. A stock solution of it, aqueous, of a known concentration must be prepared. So they want to know the known concentration. So the whole point of this is they want to know the molarity of this concentration. A student is going to titrate. That's what we do. Titration is we're going to take a known amount of another chemical, in this case an acid, and we're going to basically titrate this substance with this acid to figure out its concentration to make it known. That's the whole point. So it's really important that you read this. So since I'm titrating this substance with this acid, draw yourself a picture. This is a drop from the burette, and because I know HCl is a strong acid, and I know that because Cl negative, okay, is a spectator, so this breaks apart into H plus and a Cl negative, I know that my halogens, F negative, Cl negative, Br, I negative, typically are spectators. There's no ability of this to react with water to reform the acid. So I'm going to write H plus, and this is going to basically fall into the beaker where I have, all right, my KC6H7O2, and it still might confuse someone, but I do know this. If it's aqueous, and if I've got a metal, that K plus is going to come off, and what's basically what you're going to have is you're going to have C6H7O2 because you lost a positive K plus, and what do we know about our solubility rules? Group 1 ions are always soluble, so this will dissociate as a free spectator ion. The aqueous gives it away, but because I'm losing a positive, what remains is this compound that's negative. Now, the negative kind of gives it away because the negative can attract the protons, and this makes you understand that you're dealing with a base, and it's not a strong base. It's not a group 1 or group 2 ion with a hydroxide, so this is going to be a weak base, okay? But it's okay because I'm going to drop a strong acid onto it to drive it to completion. This is a completion type of reaction. There's no equilibrium here. Okay, so we've established, hopefully, that we understand that we're dealing with C6H7O2 negative. All right, and again, for those that are chiming in that are not part of my course, these are non-equilibrium type of acid-base problems. I'm focusing on the stoichiometry. So I'm driving this weak base by adding a strong acid that produces a lot of protons. This proton's like a heat-sinking missile for these extra electrons that this molecule has, and we're going to basically form the conjugate acid. So this is C6H7O2, no charge. Notice the total charge on this side equals the total charge. And this represents the net ion. Notice I'm not drawing the chloride ions because they don't do anything. And notice I draw the HCl separated because it's a strong acid. Notice I'm drawing this together. Why? Because if this is a weak base, this will make a conjugate acid, but this conjugate acid isn't strong, so most of it stays undissociated. That's important. So that's my net ion equation. Understand this is my conjugate base, and this is my conjugate acid. Now they kind of gave it away. The Ka for sorbic acid for the conjugate acid is that. So that kind of gave it away that you were making that. So that's the first step. All right. Now, here we go with the titration problem or stoichiometry problem. All right. They're telling me when I drop the acid, okay, onto this conjugate base, it took exactly this amount of it to completely neutralize it. The equivalence point in a titration represents the point where I have just neutralized all of the base. So as much of this that was in this beaker, okay, as much of this base that was in this beaker has been totally driven to the conjugate base by adding an equal amount of H+. You can think of these two as we added, these are both limiting reagent. You can think of the equivalence point as a double limiting reagent where we're adding equal amounts. Again, we did limiting reagent already. This is a kind of a nice way to think of it. All right, so what do I do here? Well, we've seen this before. Once I know the equivalence point, and I can know that with a pH probe, they're telling us that I'm going to find the moles of the acid that I added. Why? Because at the equivalence point, the moles of the H plus equals the moles of my base. That's what equivalence point is. So by knowing how much acid I had to add to neutralize the base, I actually get the moles of the base. Okay, so very simply, to get the moles of H plus, I know that molarity is equal to moles over liter. And if I have the volume, convert that to liters, I have the molarity, I can solve for the moles. So we've done this a million times. We've saw this in precipitation analysis. And we'll take our 0.0295 liters. I'm just converting the millis to liters because molarity is into liters. I'm going to times it by the molarity, which is 1.25, and molarity is actually moles over liter. And we can see, party people, that the liters cancel. We're left with moles, and 0.0295, okay, liters times 1.25 gives me that 0.03743 moles of H plus. One quick correction, I guess this should be 0.02995. Feel bad, now I'm over it. But in any case, that's the true conversion to liters. And same idea, multiplied together gives me the moles of my H plus. Now they're looking for this bracket represents molarity. So this equals, guess what? The moles of my base. It's the same thing. So therefore, this is the moles of my base. And I'm going to divide that, moles of my base, by the volume in the beaker. And what did I said? There was a 45 milliliters was titrated. So this is 45 milliliters. I know how many moles are in here. I know how much acid was added to neutralize this at the equivalence point. So now I know the moles of the H plus, which is the same moles. So I take the moles, this is the moles of my base, which is the same thing, and I divide by the volume in my beaker, which is 0.045 liters. Let's get rid of this. Okay, boom, boom. And now we find the molarity, moles of the base over the liters, okay? And this gives me gives me 0.832, and that's my molarity, which is equal to the concentration okay, of my base. Okay, and that's what we're after, and that's my answer. Okay, it's nothing more than that. Again, the key to this problem, and this would be a 2-point problem or a 2-point um, credit question here. They would give you a point for getting the moles of the H plus, and then they give you a point probably for recognizing it's the moles of the base. And then probably one more point to convert that to the concentration. So this could be a 3-point question. Okay, and we've seen this before. So moving forward, the pH at the equivalence point is 2.54. Well, that seems pretty low, but what are we doing here? Again, what we're doing here is we're dropping an acid into a base, which means we have a pH probe sitting in our beaker. So if we're starting with base, it makes sense that we would start with a very high pH, very basic range, and it would come down and then have an asymptote. And I probably should do that one more time. Okay, I'm coming down. I probably would come flatten out a little bit and then somewhere crash down and then come down to an N. And there would be my equivalence point, which is 2.54. Okay, now we're saying to you, what's the best choice for determining this endpoint of the titration? Now understand, the pH of the equivalence point is this right here. This is called an equivalence point. This is where the H pluses that were added equal the base that was in the beaker. The endpoint is not the same point. The endpoint is some position on this line above and below that's hopefully on this asymptote. So we're going to pick a pKa, which is really linked to its Ka, the strength of the acid, but we're going to pick a pKa that is closest to the equivalence point. And you can see that the pKa, which is the negative log of the Ka, is 2.0. That's the one that is closest. So actually, the endpoint would be somewhere in a lower pH. The endpoint, okay, is the point where the color change occurs. The endpoint is where the indicator changes color. The equivalence point is where it actually occurs. Okay? The endpoint is approximation of the equivalence point. All right? So I would pick thymol blue. Now, they say justify your answer. And you can just say that thymol blue will change color near or nearest the equivalence point. This is the only indicator where the pKa is closest to the equivalence point, and that would be your answer. So that's all they're looking for, is to say that this pKa is closest to the endpoint. Now, what that really means is that the halfway point of thymol blue between its two color changes, this represents the pH where you have 50% of the one conjugate acid. And remember, thymol blue is an indicator that's also a weak acid-base pair. So here's HIN, that's the what? The conjugate acid form. And then what it'll become is it becomes an equilibrium, I should have, as the conjugate base plus the H plus. And of course, it goes backwards and forth. And where are you going to have a color change? Well, when you have 50% of the acid and base, that's where you're going to really have that color change. That occurs at the half equivalence point when this compound actually gets titrated along with the compound. So in any case, this 2.0, okay, is tied to its halfway equivalence point. But the bottom line is the 2.0 represents, and all you got to do is find the one that's closest. Now there is a general rule, plus or minus 1 pH unit above and below the equivalence point is a good place to pick the pKa. Okay, so very simple, it really is. Next question, calculate the pH at the half equivalence point. Well, here we go. The half equivalence point would be, well, halfway between. So this would be some volume, and this would be, let's pretend this is some volume here, this would be half that volume. So the half equivalence point is the place where you're going to have 50% of the conjugate acid and conjugate base. Don't forget, in this lab, What are we dealing with? We're dealing with our conjugate base C6H7O2 negative, and it becomes its conjugate acid HC6H7O2. Now, when are they going to be same? Well, as you drop the acid onto the base, the pH drops. But you're making what? More of the conjugate base as you add the acid. And then, of course, you're doing what? You're lowering the conjugate base as you add. This point represents 100% conjugate base. This point at the equivalence point is 0%. You've driven it all the way to this. And if we do another color, magenta, in the beginning you have 0% conjugate base, conjugate acid, sorry, this guy right here. And at the end you have 100% of the conjugate acid. Where would you have 50? Right in between. And what do we know? That the pH at this point where you have equal amounts is equal to the pKa. All right, the Henderson-Hasselbalch equation, the log of equal values would go to 0 and pH equals pKa. So the question is, what's the pH? Well, if I knew the pKa, I'd be great, but I don't. But what do I have? Oh, they gave me the Ka. So if the Ka is equal to 1.7 times 10 to the negative 5, to get the little p, that means I just do negative log. So the negative log of 1.7 times 10 to the 5 is 4.8. So that must be that pH right there, 4.8. All right, so 4.8 is the answer because all I did was negative log of the Ka, which was given to me. And negative log of the Ka is going to give me my pKa, which is going to equal the pH at the what? Half equivalence point, because that's where you're going to have 50% of both your base and conjugate acid. That's important you realize. All right, so very simple there. 4.8, all I did was negative log of the Ka that was given to me in the problem above. Okay, moving on up. So now we have a graph of what we're dropping. Remember, we're dropping the proton, okay, onto my base. So we're starting with an initial pH. So they say the initial pH and the equivalent point is marked below. Okay, well, I know that I'm going to go through the halfway equivalence point that I just found out to be 4.8. Okay, so if the equivalence point or the equivalent volume is about 30, it took 30 milliliters of the acid to neutralize the base, then somewhere near 15 is the halfway equivalence. And I just found out that pH is 4.8. So I find my 4.8, and that's about right there. So what I need to do is I need to draw a line, okay, that will intersect that. But I just can't draw a straight line. This is going to come down, level out a little bit, and then asymptotic drop. Okay, and that's what I'm expected to do right there. And I'm leveling out here because I'm making a conjugate acid-base pair. It's a buffer. We'll talk about this. This comes down, and you need to show an asymptotic change, a sharp decrease near the equivalence point. It really should go through that line, okay? And that's what they're looking for there. Pretty simple, but I'm using my understanding of the half equivalence point, and I had to start with what? I had to know if this is my equivalence, then this point goes through half that value. Okay, very important that you get that. Not hard. All right. A more difficult question is, what's the final pH? And then complete the sketch. Well, I know that at this point right here, the what? The H pluses that I added is equal to the base in the beaker. So the final pH is just going to be the extra H pluses that I add beyond that. So let's go find the moles. Well, I added it till it was 40. I said I added 40 milliliters total. The equivalence point was 30, so the extra acid I added was 10 milliliters. Okay, let's go find out how many moles of acid that was for that concentration. Let's go find its concentration of H pluses. And once I find that, I can easily find a pH by doing negative log. So I'm going to take 0.010 liters. I'm going to times it by the molarity, so I have to be in liters. I'm going to times it by the concentration of the acid. They told us it was 1.25, and that's moles per liter. Okay, liters go bye-bye, and I'm going to get total moles of my acid, or my H plus. So I get a value of 0.0125 moles of acid, or H plus. And on with the concentration. So I'm going to divide by the liters. Now careful, you're not going to divide by 10 milliliters. You're not going to divide by 40. What just happened in this lab? We started with a total of 45 milliliters in the beaker. We added 40 more. This is the volume of HCl added. So I added 40 more total. So I got a total of 85 milliliters. Convert that to liters, 0.085, and that's going to give me moles over liters, the molarity. And what I get, party people, I get 0.14705, and that's my molarity of my what? Protons, H pluses, or H3O pluses. What do I want? I want the final pH. To get the pH, I do negative log of 0.14705. And what I get is a pH equal to 0.83. So my final pH, okay, is going to be 0.8, something like here. And remember, I asymptotically going through this, and then I'm going to level off. And that's how I'd finish that. Okay, last little piece. The pH of the soft drink. So this is actually not in a titration, is 3.37 after the addition of, I guess, exactly that amount of base. Which species, the conjugate acid or the conjugate base, has a higher concentration? Well, we know that this is 50% conjugate acid and 50% conjugate base, A negative. I'm just going to use that. Okay, now at 4.47, or I should say we calculate this to be what? 4.8, I should say. So at 4.8, that pH is when they're equal. Well, if I keep dropping acid, then I'm going to keep converting my base in the beaker into more conjugate acid. So this is going to get bigger as this gets used up. So the conjugate acid is going to be in higher quantity. So you could say that the concentration of the conjugate acid, C6H7O2, is greater than the concentration of the conjugate base. Because when you add more H plus, you drive the reaction to make more conjugate acid, okay? Or you could say something like the concentrations of the conjugate acid and the conjugate base are equal at the half equivalence point. A pH of 3.37 is lower than that of the half equivalence point, so the protonated form, okay, has a higher concentration because you're driving it forward. Many ways to do that. So I hope this helped.